I'm Bhrigrish Mishra, a PhD student at IIT Bombay, and this is the online session of Elements of Solar Energy Conversion Week 6. So, in this online session, I'll briefly talk about the basics of flat plate collector, which has already been seen in the video. And then in this lecture, we'll mainly focus on the transmissivity and absorptivity of cover system of flat plate collector, and the rest will be covered by Mr. Pawan Kumar, whose online session will be held tomorrow at 6 to 7 p.m. same time. Okay, so as we have already seen in the lecture that a flat plate collector is a simple device who absorb solar radiation, and like this is basically a thermal device, like who utilizes solar thermal energy. Okay, or in a simple language, it absorbs solar radiation and use it as a thermal energy. Okay, so so the main components of a flat plate collector is this is the glass cover. So the main component of the flat plate collector is this glass cover. Okay, this is, I'll start with the the main component. So first is, since solar radiation is coming and we want to capture the solar radiation in order to generate the heat, or I can say we want to convert solar radiation into thermal energy. So for that, first we need to capture the solar radiation. So that is why we have the absorber here. Okay, so this is the absorber here, this is the absorber, and then when it absorbs the radiation, we need to collect this thermal energy to some liquid, okay, via some liquid. So for that we need water. So water is circulated in this pipes. Okay, these are the metallic pipes, and now so absorber plate absorbs the incoming solar radiation, and then the temperature of absorber plate increases. So as temperature increases, it also starts radiating the energy, okay, which corresponds to the that you can calculate from the Wien's displacement law, that depending upon the temperature the body radiate energy in a certain wavelength. This is the peak wavelength at which the body emits energy for a certain temperature T. Okay, so we don't want to we need to avoid this loss, because if it goes to the outside, then the useful heat will be very low. So for that we use a glass cover. Okay, this is a glass cover. So the property of glass is that it is highly transparent in solar radiation. This is glass cover. So it is highly transparent in solar radiation, so that it allows the solar radiation, either direct or diffuse, both. Okay, it utilizes both the radiation. So the glass cover helps to come the solar radiation to the absorber plate. But the absorber plate, when absorber plate temperature increases and it starts radiating the heat, then this glass cover do not allow these radiations to go outside the atmosphere. Okay, it traps this heat, so heat cannot go outside this glass this system, and thus absorber plate has a certain temperature. Okay, you can say a steady state temperature if the environmental conditions are remain same. that means the airflow, temperature and the solar radiation are same, then it will attain a constant temperature. Okay, but there are, this is the radiation loss. Okay, there are other losses also, like convection losses. So convection loss is only possible when there is a medium which take away the heat. So in this case it is air. So in order to this glass cover also helps to reduce the convection losses, because then the air inside this chamber will not directly interact with the air. So the convection, this glass cover also helps to reduce the convection losses. There are other losses, for example conduction losses can also happen. So for that we have this insulation. Okay, this insulation which reduces conduction as well as convection losses. Like if it is highly conductive, then heat can flow from this absorber plate to the outer surface, and then convection loss will occur. But that is why we use this insulation, so that so insulation means thermal conductivity is very low. Conductivity is very low. Okay, so this is the basic design of a flat plate collector. Now how we can carry out or take away this heat? So that is why we have this tubes. So this is a storage tank, so water storage tank, and it has cold water. Okay, so this way water goes to the tubes, and tubes are interacting with the absorber plate, which is at a high temperature. So these water absorbs this heat via conduction, or you can say radiation also, and then this heat, this hot water flow into the storage tank. Okay, so it keeps circulating. So the upper portion will have hot water, and the bottom portion will have a cold water. Okay, and that's how we get hot water. So this is used in the used for the domestic hot water purpose. The same principle also follows for the air heater or any other flat plate collector devices. It can be used for the multiple applications. Okay, so now the first question is, what is the condition of stagnation temperature in flat plate collector? So what do you mean by stagnation temperature? So first we can look the useful heat gain by the flat plate collector. So useful heat gain by the flat plate collector, it is simply Qu dot equals to AC. AC is the area of collector, S minus UL TPM minus TA. Okay, yeah, so this S is the absorbed energy, like solar radiation energy absorbed by the absorber plate, and this is the losses occur due to conduction, convection or radiation. So in a more simple way I can write it like Qu dot equals to ACS minus QL. Here this QL represents the heat loss. Okay, so if there is no water flow, okay, if there is no, or I can say liquid, there is no liquid flowing, okay, in the FPC, then useful heat gain 0, then Qu dash will be 0. So it is ACS minus QL equal to 0. So AC into S equals to QL. So if we solve this equation, we get a temperature, and that temperature is the TS, or stagnation temperature. So basically stagnation temperature is the highest temperature that the absorber plate can attain. So that means when the absorber plate attain this temperature, it won't take any extra heat or any heat from the solar radiation. That means now it will not absorb the solar radiation anymore. Okay. So after this, it won't absorb any solar radiation, or in a simple word I can say, or in a simple word, at stagnation temperature, heat gain by the absorber plate equals to heat loss by the plate. Okay, so it means what does it mean by that? It won't absorb any heat. That means whatever it is absorbing, it is radiating, or it is lost in the surrounding. That means it remains at the same temperature, and that is called the stagnation temperature. So stagnation temperature helps to compare different FPCs. Okay, stagnation temperature helps to compare different FPCs. Okay, so the next question is, obtain the expression for the transmissivity of the cover in FPC. Okay, sorry, this is only FPC, not considering. So basically here we want to explore the properties of the cover, glass cover, which we are using to avoid radiative losses in the flat plate collector. Okay, because so it has a certain refractive index around 1.5. so whenever there is a mismatch in the refractive indices, for example, this is glass, okay, and this is air, so air has refractive index 1, glass has 1.5, and again air has 1. So whenever there is a mismatch in the refractive index of the two medium, then there will be some reflection losses. Okay, that means whatever the solar radiation is hitting on this surface, depending upon the difference between these two mediums, some portion of solar radiation will be reflected back. Okay, that means this is the loss which we are not considering in the calculation of the useful heat gain of flat plate collector, but this is the loss. And there are several research going on or has been done to how to avoid this surface reflection losses. So that is why there are coatings, anti-reflection coatings has been introduced. Anti-reflection coatings. So what does these anti-reflection coatings do? So they try to reduce this gap, either simply using some material technique, or they have a special kind of a structural design which traps the heat. There are a lot of ways. So the main motto is we need to reduce this reflection as much as possible, okay, so that maximum amount of solar radiation can reach to the absorber plate. Okay, so we will study the transmissivity of the cover in flat plate collector. So so now glass can have both absorption as well as reflection. So considering reflection, refraction and absorption separately. So the glass can have both reflection as well as absorption simultaneously, but here to calculate the transmissivity of the cover we are considering these two individually, okay, and then we combine. So transmissivity of the cover tau is tau r into tau v. Okay, this tau r is transmissivity considering reflection, refraction only, and this tau is transmissivity considering absorption only. Okay, so tau equals to tau r tau a, this is the transmissivity of the cover, and tau r is transmissivity considering reflection, refraction only. Tau v is the transmissivity considering absorption only. So we will derive, or we will see what are the formula for these two quantities separately. Okay, so first we will look for the tau r. Okay, tau r. So suppose this is so we want to check at the interface between air and glass. Suppose I have N1 this and N2, two medium 1 and medium 2. So and this is normal. So if air hit like this, then there will be some reflection at the same angle theta 1, okay, and there will be some refraction at angle theta 2. So suppose this is incident IB and this is reflected IR. So according to Snell's law, according to, you all have studied Snell's law in 12th. According to Snell's law, N1 sin theta 1 equals to N2 sin theta 2. So if we know the medium refractive index of the both medium and incident angle, then we can calculate the refracted angle theta 2. Okay, Now uh, solar radiation is nothing but the electromagnetic wave. Electric wave, it is a combination of electric and magnetic wave. So it has two polarization. So since it is a wave, so polarization means in which direction it is oscillating. Okay, so this is the direction of oscillation, means this is the polarization direction. So since it has electric magnetic wave both, it has two polarization. Okay, it is called a TE wave, and TM wave, and depending upon the surface, the reflection and transmission for TE and TM wave can be different. Okay, so in this case, if you want, you can look the Fresnel's equation, okay, to know more about the reflection transmission by the TE and TM wave on this kind of medium. Okay, here we will simply write the formula for the two reflectivities. Okay, so suppose two medium, first and second. Okay, so reflectivity for medium first written as rho first, not for medium but for the first polarization. Rho first equals to sine square theta 2 minus theta 1 by sine square theta 2 plus theta 1, and for second, okay, it is tan square theta 2 minus theta 1 by tan square theta 2 plus theta 1. So total reflectivity is IR by IB. IR here is our reflective wave, and IB is the incident wave or incident beam. So IR IB, and this is nothing but the average of both the reflectivities, rho first plus rho second. Okay, so now I got the reflectivity. I can calculate the transmissivity. Okay, one thing, when incident angle is 0 degree, okay, for theta 1 equal to 0 degree, both the reflection will be equal and equal to the total reflectivity. So in this case, rho equals to rho first equals to rho second, and this is nothing but n1 minus n2 by n1 plus n2 whole square. Okay, so now we calculated reflectivity, we have to calculate the transmissivity. So in the same, since we have two reflectivity for first wave and for second wave, similarly we will have two transmissivity for first wave and for second wave. So transmissivity tau equals to half of you can write tau r, so half of tau r first plus tau r second. So now we need to calculate this tau r, and since in actual case there will be two interfaces. Okay, this is, suppose this is glass, I can write in the middle. So this is glass and refractive index say n2, and this is air n1, and this is again air n1. So there will be two interfaces. Okay, so reflection occurs at both the interfaces. So suppose beam is hitting on this surface, so consider it as a 1. Okay, we are just taking the unit. Okay, so it is 1 unit radiation is hitting on this surface. So the reflectivity here we are considering the rho first. The reflectivity is rho first for this case, and in the same derivation will be applicable for rho first also. Okay, so we are considering the reflectivity rho first here. So this, there will be some reflectivity at this interface, it is called rho first, and then the remaining, that is 1 minus rho first, will be transmitted. 1 minus rho first will be transmitted. Then again there is this glass air interface at the bottom. Okay, so consider it as a 1 and as a 2. Okay, so then again there will be some reflection, and this reflection is also rho first. Okay, so it is rho first into 1 minus rho first. Now it is 1 minus rho first, and then again reflection was rho first, so the transmission will be 1 minus rho first whole square. Okay, now again there will be some transmission here. What is rho first 1 minus rho first square, and then again reflection here. So this is again rho first square 1 minus rho first. So again reflection on this surface, then there will be again transmission, and this is again rho first square 1 minus rho first. So if you do this further, you will get rho first to the power 4 1 minus rho first square, and so on. Okay, so we need the transmission. What is the transmission here in this case? So it is tau r first equals to, adding all these things, 1 minus rho first square plus rho first square 1 minus rho first square plus, and so on. So taking 1 minus rho first square common, it is 1 plus rho first square rho first to the power 4 rho first to the power 6, and so on. So it is an infinite geometrical series, and whose sum is, and since here rho is less than 1, or I can say 0 less than rho first less than 1, so this sum can be written as minus rho first square by 1 minus rho first square. So if you solve this, you will get simply 1 minus rho first by 1 plus rho first. Okay, this is the tau r1 r first, and similarly you can calculate tau r2, which is also 1 minus rho 2 by 1 plus rho 2. Okay, so and so in this way we can calculate total reflectivity, that is half tau r first plus tau r second. So what if there are m number of layers, like you have seen that there can, like glass covers can be increased. In the best case scenario, there will be 2 glass covers in a flat plate collector, but it can be more. Okay, so for m glass, so how to get the formula for the m glass covers? So similarly we can obtain for m glass covers, tau r first will be 1 minus rho first by 1 plus 2m minus rho first, and similarly tau r second equals to 1 minus rho second by 1 plus 2m minus 1 rho second. Okay, so this is a straightforward formula, Now we need to calculate uh, for the tau wave, because as you remember the total transmission tau equals to tau r into tau wave. So we got the tau r from this relation. Okay, now we need to calculate tau wave. So tau wave represents the transmission occurs due to absorption. Okay, so for example, suppose I have I'm considering a small thickness dx, okay, and the incident radiation is I, okay, and the outgoing radiation is I plus di, okay. So in this case and since radiation is reducing, that means di is negative. So in that case this change in the di means change in the radiation is proportional to or is simply equals to, so there is the property of this absorption property of this medium called extinction coefficient and denoted as K. Okay, so this extinction coefficient is in unit of, it is per unit length. Okay, and this is responsible for the absorption losses inside the medium. So this di is proportional to minus K times I dx. Okay, and we can rearrange this and integrate this. So di by I, and I, suppose the incident radiation is II and the outgoing radiation is IO. So this is equals to minus K. Now thickness is suppose 0 to L is the thickness. L is the thickness of the glass cover. So we can simply calculate ln. This is the simple integration which you can do. IO by II equals to minus KL. Okay, so in this case I can write transmission tau wave is nothing but outgoing radiation upon incident radiation, which is I naught by II equals T to the power minus KL. Okay, this is for the normal incidence. Okay, for other than normal incidence, this L will be changed to L by cos theta 2, where theta 2 is the refraction angle, because then L will be increased to L by cos theta 2. So tau wave will be e to the power minus KL by cos theta 2, and for M covers it is tau equals e to the power minus M KL by cos theta 2. Okay, so this, so now we have tau wave and tau r, so we can easily calculate tau equals tau r into tau wave. That means the total transmissivity of the glass cover. Okay, so this is the last question I have considered for this online session. So calculate the transmittance absorptance product for beam radiation for a flat plate collector with two glass covers each 4 mm thick. The incidence angle is 30 degree and the value of the extinction coefficient is 4 meter inverse. Take the value of alpha for the absorber plate to be 0.86 and the refractive index to be 1.526. So here we need to calculate the transmittance absorptance product. So transmittance absorptance product for beam radiation tau alpha b, and the formula for this is tau alpha by 1 minus alpha into rho d. Okay, here rho d is the diffuse reflectivity. Okay, subscript d means diffuse of the cover system. So to calculate diffuse reflectivity of the cover system, we can follow the same procedure which we follow for the beam radiation, but for this case, for diffuse case, we can simply consider incidence angle 60 degree, because we assume that sky behaves as an isotropic and all the diffuse radiation on the glass coming at the angle of 60 degree, okay, or simply behaving as a beam radiation and hitting the surface at an angle of 60 degree. So considering theta 1 equals to 60 degree, we can calculate the diffuse reflectivity by following all the methods we use, all the steps we use to calculate reflectivity for beam radiation, okay, or beam reflectivity. So we need to calculate transmittance, absorptance for this system. So what are the things given here? Okay, so given theta 1 equals to 30 degree and glass cover, 2 glass cover, so m equals to 2, and thickness of each glass cover is 4 mm. I can convert it into meter. It is 4 into 10 to the power minus 3 meter, okay. And the extinction coefficient of the glass, that means K is given as 4 meter inverse. The value of alpha, that means the absorptivity alpha, is given as 0.86, and refractive index of glass, that means Ng, is given as 1.526. So we have all the information. So first we will calculate the tau, okay. So as we have seen earlier, for tau is half of tau r first plus tau r second, and tau r first and is 1 minus rho first by 1 plus 2m minus 1 rho first, and similarly tau r second is 1 minus rho second by 1 plus 2m minus 1 rho second, okay. So and we have seen the formula to calculate rho first and rho second. Here rho first is the reflectivity by one polarization and rho second is reflectivity by second polarization by the air glass system, okay. So rho first is we have, so first of all we need, so yeah, rho first is sine square theta 2 minus theta 1 by sine square theta 2 plus theta 1, and rho second is tan square theta 2 minus theta 1 by tan square theta 2 plus theta 1, okay. So we have given theta 1, we need to calculate theta 2. So theta 2 can be calculated using Snell's law, n1 sine theta 1 equals to n2 sine theta 2. So sine theta 2 equals to n1 by n2 into sine theta 1. So theta 2 equals to sine inverse n1 by n2 into sine theta 1. So if you put all the values, you will get theta 2 equals to 19.126 degree, okay. Now we have theta 2 and theta 1 is given 30 degree. You can easily calculate rho first and rho second. So the value of rho first is 0.062 and value of rho second is 0.0276, okay. So we have the rho first and rho second. We can calculate tau r first, and it is simply 1 minus 0.062 by 1 plus m equals to 2, so it is 2 into 2 minus 1, and again 0.062. so tau r first is 0.791, and similarly we can calculate tau r second, which is 0.898. okay, so we have tau r first and tau r second. Now we can calculate tau, the transmissivity of the glass cover system. So tau equals to half tau r first plus tau r second, and it gives 0.8445. okay, sorry, this is tau r. okay, this is tau r. So first, so now tau r we have to calculate tau a. okay, so for tau a is simply e to the power minus m k l by cos theta 2, and we have all the values. So it is e to the power minus 2 into k is 4, l is 4 into 10 to the power minus 3 cos 19.126 degree. So if we solve, the transparency of due to absorption is 0.966. okay, so we have tau a, tau r. Now we can calculate transmissivity tau, which is nothing but tau r into tau a. So tau r we got 0.845, and tau a is 0.966. so it comes out around product 0.816. so we have tau, and the alpha is also given to 0.86, but we also have to calculate rho d, okay, the diffuse reflectivity, this term. So in order to calculate diffuse reflectivity, we need to follow this procedure again, but considering incident angle as 60 degree. okay, so calculation of rho d. So in this case theta 1 is 60 degree. So again, using Snell's law, we can calculate theta 2 equals to 34.58 degree. Now following the again same procedure which we did here, rho first, rho second, we need to calculate. So rho first is around 0.185, and rho second is very less, 0.00145. so this is what I was saying earlier, that the two polarizations can be have two different polarization beam can behave differently when it hits to the glass surface, or depending upon the incident angle, or even if you change the it also depends on the surface. Like for the same surface, for same incidence angle, they have different reflectivity. For example, in this case, first has 0.185 reflectivity, but second has 0.00145, which is very low. okay, so we can calculate tau r first, and it comes around 0.524, and tau r second is 0.994. so tau r comes around 0.759, and similarly we can calculate transmissivity due to absorption. So it comes out around 0.9618. okay, so now we need to calculate the reflectivity. So the formula for the diffuse reflectivity rho d is tau a into 1 minus tau r. okay, so earlier for the transmissivity we were using tau A into tau R. Here for the diffuse reflectivity we simply use tau A into 1 minus tau R. Okay, so it is it comes around 0.2317, and earlier it has been seen that for a normal, like for a standard glass, that means refractive index 1.5 and K is also around 4, this rho d comes out around 0.21 for a 2 glass cover system and around 0.15 for a 1 glass cover, and we are getting 0.2317, so which is similar to 0.21. Please note that here we have used n equals to 1.526, so that may change the theta too, but yeah, it is close to the standard value, which is 0.21. So now we have all the results, all the values. We can calculate the transmittance absorption product, which is tau alpha b, and in this it is tau alpha by 1 minus alpha into rho d, and tau alpha is given as 0.702 divided by 1 minus alpha is given 0.86, and rho d we have calculated 0.2317. So tau alpha b is 0.7255. okay, so that means this is the transmittance absorptance product for this question. And where do we use it? We use it to calculate the S. What is S? S is the solar radiation absorbed by the absorber plate. This is for the beam. Similarly, we can calculate it for the diffuse also. That means we can consider again incident angle to 60 degree for all the calculations, and we can calculate for that also. For tau alpha b it comes around 0.62 or 0.64 something. You can do the same problem for different angles, like for theta 1 equals to 45 degree, theta 2 equals to 60 degree. I have picked this question from Sukhatme book. Okay, problem I think 4.3 or 4.4. So it was asked to do the calculation for 3 different angles: 30 degree, 45 degree, 60 degree. So I have shown you for 30 degree. You can check for 45 degree and 60 degree also. So theta 160 degree. So yeah, that's it for today. So today we have solved 3 questions, like we calculated transmittance absorptance product for the given value, and before that we have checked how to calculate the transmissivity of the cover in flat plate collector. We derived some expressions to calculate transmittance and absorptance for a glass cover system, and we have also looked what is the condition of stagnation temperature, what is the stagnation temperature, and earlier we have saw the basics of flat plate collector. So yeah, that's it for today's